Welcome back, chemistry fans. Today, what we're going to do is Unit 2. Technically, it's Topic 4 in your notes, but I believe we're kind of referencing this as Topic 6 so that each one of the days reflects a different topic that we uniquely talk about on that day. Today's topic is going to be about the shapes, the molecular shapes. So in the previous topics, we've talked about electron dots, how we represent the valence electrons on an individual element. Then we talked about the Lewis structures, how we can bring it together to represent the bonding in molecules. Well, now that was a two-dimensional representation. We're going to try and blow it up into 3 dimensions so that you can start picturing it in your mind as it actually is in the real world. So let me share with my screen. We're going to jump right into it. So if you're unfamiliar with how to deal with a Lewis structure, we're going to need you to get some references back on the previous topic to do that. Now, what you'll notice is there's an acronym over here on the left, the title, VSEPR. I will tell you what that stands for. Over on the right, what I want you to start noticing is there are 2 molecules here that you are familiar with, water and carbon dioxide. One of them, however, is bent in nature. It looks like a chevron, while the other one is a linear molecule. And I don't know why that is the case. We haven't explained why one would look different from the other. They both have 3 atoms. Why wouldn't they all just be the same? Why would there be this 180-degree angle between the molecules? Or why is the other one approximately 109.5? Well, we're going to try and explain that today. So what does VSEPR stand for? It stands for valence shell electron pair repulsion. The big key there is the electron repulsion. That's what we're going to focus on. If we have extra electrons from our Lewis structure, that is going to put repulsion pressure on the bonding electrons, causing the molecule to bend in that 110-degree chevron look feel to it. So we're going to try and see how we can prove that, explain that. One of the terms that pops up for that electron pair repulsion is something called an electron cloud. So instead of always referring to them as extra electrons or unpaired electrons, you might hear them being referred to as electron clouds, electron densities, places where electrons are likely to be found because we have drawn out the predictable Lewis structures. Okay, so now what does this mean to you? There are a bunch of different shapes. However, we're not going to be responsible for all of them. So just be aware that there are many different shapes out there, and there are some similarities of their names. You'll notice that there are bent molecules and linear molecules that happen to pop up. Even though there are different numbers of atoms, they still end up being in a similar shape. And we'll have to get to explaining that one. So let's jump into what you are actually responsible for. There are 5 different names that you must know. Now, I understand there are 6 pictures here, but if you will notice the 2 linears on the left, they have different numbers of atoms, but they have the same name. So there's still only 5 molecules names that you must be responsible for knowing. The 2 on the top left, linear. On the right-hand side, we have Trigonal Planar. Couple that with Trigonal Pyramid. They seem to have similar names. The only difference between them is this little green dot on top. That green dot actually represents unshared pairs of electrons, an electron cloud. Well, the bent and the the bent and linear, the only difference between those 2 are these unshared pairs of electrons. So now we're starting to see a difference between molecules. If we have unshared pairs of electrons in an atom that has in a molecule that has 4 atoms, we know that it will be a trigonal pyramid. If it doesn't have the extra electrons, if it were to have a double bond, it would be trigonal planar. If there were a double bond in a molecule that has 3 atoms, it's going to be linear. If there is unshared pairs of electrons on a other 3-atom molecule, it's going to have a bent shape. Tetrahedral stands all to its own. It does not have any complementary contrasting molecules. It's just, if it has 5 atoms, it's tetrahedral. If it has 2 atoms, it is linear. All right, well, let's jump into the proof. How do we know which is which? What you're going to have to focus on in the Lewis structure are those unshared pairs of electrons. If we have unshared pairs of electrons, lone pairs here, what we are seeing is that's going to cause the molecule to force the bonds to bend. So the bonding pairs that they're talking about are inside of these lines that we will draw for the Lewis structures. So the lone pairs will push on the bonding pairs of electrons. Jump into the first one. It's simple. We can do the Lewis structure. We have 1 minus half. The 1 for each of those is 8. That's a total of 16. The half for each of the nitrogens is 5. That's a total of 10. Subtract those 2 values, and you get 6. So I know that if I divide that by 2, I have 3 bonds. I have just found out that there is a triple bond between these 2. But it really didn't matter because there's only 2 atoms. And from the previous images, I know that anytime I have 2 atoms, it will be linear. Linear. Oh, that's not even, well. Take your time. There it is, linear. That's the goal of this unit, be able to tell me what the shape is. So let's jump into a couple more examples. NH3. I know that the first element listed will always go in the middle of the symmetry. It does not matter if I put my H's on top or on bottom. I'm going to put them on bottom just in case if there's an extra electron that causes it to bend, it will look more like the structure that we have tried to represent in the previous images. I'm going to do 1 minus half for each one of these. 1 minus half. So there are 1 nitrogen, it wants 8. There are 3 hydrogens, they each want 2. That is a total of 14. The half on this one, each of the hydrogens has 1, the nitrogen has 5. That is a total of 8. The difference between those is 6. Divide that by 2, and I get my answer of 3. That means that there are single bonds. The nitrogen does not have a stable octet, so I must include a little ghosty electron cloud on top, which causes repulsion of this molecule, which means that it's going to bend downwards. It's not got the name bent. Instead, because it has 4 atoms, we're going to call it Trigonal Pyramidal. It's going to look like this. Okay. Now, let me jump down to SCl2. I know the first element goes in the middle. I know the CLs go on the side. Now, here's one thing that I want to go ahead and help you with, make this a little bit easier. I want to highlight the fact that all elements that are halogens are going to have single bonds. Halogens are in the 17th column. They have 7 valence electrons. They need to have only 1 new electron. I can't add 2 or 3 because they only need 1. If I look at chlorine, it has 1, 2, 3, 4, 5, 6, 7. And so when it creates a bond, it only needs 1 electron. That means it's only going to take some electron, 1 electron, share 1 electron with 1 other material. That means it's only ever going to have a single bond. The same is true for hydrogens. Hydrogens and halogens always have single bonds. Therefore, you do not need to show your work on how to draw the Lewis structure for halogens or hydrogens, because I know they will guaranteed only have single bonds. Sulfur does not have a stable octet, so it's going to need some extra electrons. Now, I'm going to just put them all up on top. I can put them on top and bottom. It's fine, but it's going to be easier for you to understand that there is repulsion going on if I put them on top. You might think that if they pushed up and then the other ones pushed down, that they would even out and be level, and that's not the case. So what happens instead is, again, this molecule ends up being bent. And in fact, this time the shape name is called bent. CBr4. Br is also a halogen. So it does not require any extra work from us to show how it bonds, because I know that all of the bromines are going to have single bonds. I see that all of the carbons octet rule is satisfied. So this is going to end up being a tetrahedral molecule. The reason why I draw a solid triangle is to try and emphasize the fact that that first atom is coming out of the page towards you in the camera. Same thing is happening with my trigonal pyramid. There's a solid triangle and it's coming out of the page towards you. So this name of this shape is called tetrahedral. I got one more to go, and it's this NO3. Now, this one, I do need to draw the structure because it's not a halogen, it's not a hydrogen. So I've got to put my N in the middle. I'm going to surround it by oxygens. My want is 8 times 4. Every atom wants 8. There are no exceptions to the rules. That's 32. The have now is different. I've got 4 atoms. They each want 6, but I also have added one more additional electron. That's what the -1 means. So what I in fact have in this case, oh, that shouldn't be there. Oh, sorry, I've got a nitrogen. I don't have 4 times 6. Let me try that again. So I've got 3 times 6 for the oxygens, and then I have 1 nitrogen, and I added 1 for that extra electron. Now I have 4 times 6, which is 24. Subtract those 2 values, and you get 8. That means I've got something weird going on. I've got 3 bonds, but now I have to share a 4th bond somewhere. It does not matter where you place it. The term to explain this is called resonance. It's called resonance. Resonance means that there's a fluctuation of where this double bond goes. It could be on the left in the same next moment. It could be on the right. It could be over here on the right. It does not matter where you place it because there is resonance, and all 3 of those positions are equal to one another. So just place it down somewhere. It is called resonance. We will try and practice that a little bit later in another topic soon. Generally speaking, you're supposed to put brackets around this to remind everyone that you did add 1 electron, and that's the reason why it worked out perfectly. Okay, this is everything that I wish to share with you about the VSEPR molecular shapes. Thank you for staying attention. I will talk with you again soon. Farewell. Goodbye.